Here in section 3.8, our goal is basically to take this whole idea of partial derivatives or partial differentiation and relating it to word problems specifically. It's kind of taking the rate of change, the whole concept of derivatives, and putting it into the real world situations. And so concepts we're going to be looking at are things of like you have a cone, and as you put in water in the cone, does the diameter expand? Or if you're in a balloon, if you start blowing air into the balloon as the diameter is expanding. So things are changing. You've got a flow coming in, you've got a diameter changing. It's all about these rates of change. So here in example 1, we're just going to kind of warm up to this whole process. And we want to suppose that the radius r and the surface area given by this equation of a sphere is our differentiable functions of t. Okay, so that's good to know that we're differentiating with respect to t. And we want to write an equation that relates ds dt to dr dt. Okay, so let's get started. First of all, what I'm basically going to be doing is the fact that r and s, that they're both differentiable functions of t. So if there's not an r variable or an s variable, everything else you can almost treat as like a constant. Okay, so over here on the left, then we're going to take ds, the derivative of the surface area with respect to time, is going to equal, remember, like anytime you're taking a derivative, if it's got like coefficients to it or any kind of constants, we pull it off. Okay, so I'm just going to kind of pull that off, and then let's look at taking the derivative of r squared with respect to time. So it's going to be 2r to the first, and then dr dt. Okay, so altogether, we'll have ds dt is equal to 8 pi r dr dt. And right there is an equation that relates ds dt to dr dt. So the change in the surface area with respect to time is going to equal 8 pi r times the change in the radius with respect to time. Okay. So it's just kind of like, hopefully y'all are seeing real quick before I go on. Hopefully y'all are seeing how, when we were looking at before, if I said y equals 2x squared plus x, when we were taking the partial derivatives or the partial differentiation, let's treat y squared. We wrote it as 2y dy dx, and then equals 4x, and then we did dx. It's just this time, instead of taking the derivative with respect to x, we're just doing it with respect to almost like another variable, time. Okay, so in example 2, if x is equal to y cubed minus y, and dy dt equals 5, and dx dt, we want to find that when y equals 2. Okay, so coming down just piece by piece, we're going to be, obviously, since it says like dy dt and dx dt, we're going to be taking a derivative with respect to time. So the derivative of x is just going to be 1, but then it's going to be 1 dx dt. The derivative of y cubed would be 3y squared dy dt, then minus 1 dy dt. Okay, or we can look at it as just taking off the ones. Dx dt is equal to 3y squared minus 1 dy dt. And so in this problem, if they asked us just to find the relationship between dx dt and dy dt, this would be it. But further, to kind of keep going on to even just the next step of what we're going to be seeing in these word problems, is going back to some given information. So it's saying the change in y is going to be 5 when y equals 2, so we want to find dx dt. Okay, so just finishing up this a little bit more, so taking the next step further, then dx dt is going to be 3 times 2 squared minus 1 times dy dt, which is 5. So 3 times 4 minus 1, and then times 5. And this will give us an answer of dx dt equals 55. And that's what we're looking for. Okay, so to start this problem, what we're going to be doing is, obviously they tell us right here, we're going to be taking all of the derivatives of each of those variables with respect to time. So the derivative of r is going to be 1 dr dt. The derivative of s squared would be 2s ds dt. V cubed would be 3v squared dv dt. And then the derivative of 12, since the constant, will be 0. So going in and plugging the information that we know dr dt is 4. So 4 plus 2s is 1. ds dt is negative 3 plus 3. We don't know v right now, so we'll just keep it as v squared. And then dv dt we're going to leave right there because that's what they're asking us to solve for. Okay, So taking the information that we know right now, basically 4 plus negative 6 would be a negative 2 plus 3v squared dv dt is equal to 0. Or if we solve this for dv dt, what we'll get right now will be 2 over 3v squared. Well, we actually want to get an answer, so how can we get v from the problem? Let's go back to what's given to us. We know r is 3 and s is 1. So if we go to the original problem, and if I know 2 of the 3 variables, shouldn't I be able to get the third one? In a sense of, it says r plus s squared plus v cubed equals 12. Let's just solve this for v cubed real quick. So obviously 12 minus 3 is 8, minus 1, so v cubed, 12 minus was 3 minus 1, so it's already taken care of. It's 8 for us. It's like it should probably come out nice and pretty for us. But then by the time we take the cube root of everything, we'll get v to be 2. Okay, so let's go back to our problem then. Then we know that dv dt is equal to 2 over 3 times 2 squared. And wrapping it up then, 2 over 12 will give us an overall answer of 1/6. All right, let's go on to the first example that uses our book. Okay, so instead of me actually writing out the whole entire problem, if y'all will do me a favor real quick and just pause this, go grab your books, read the problem in the book, kind of get an idea, just read through it about 1 or 2 times. So I'm going to just jump in talking about it right now, and you'll get completely lost if you have no idea what I'm talking about. So if y'all will just take 2 seconds, get out your book, read the problem, and then hit play again, and we'll pick right back here. Okay, so to start this problem, in part A, what they're wanting us to do is how to figure out how does dv dt relate to dh dt if r is constant. Okay, so if you look at our main equation, our volume equation, we have v, r, and h. We have 3 variables. And right now they're wanting to tell us, okay, what if r is actually a constant? How does v basically relate to dh dt? Okay, so let's go through and just take our derivatives. So dv dt is equal to, and since r is constant, you can almost treat that like the 1/3 in the pi. So we're just going to pull that off to the front, 1/3 pi r squared. And then right there, the only other variable on the right side is h. Well, the derivative of h, just as coefficient is 1, but then dh dt. Okay, so if we kind of just put this together, then really, without that bracket in there, it's dv dt is equal to 1/3 pi r squared and then dh dt. So what this problem would represent would be like in a word problem specifically, if it said, if the radius was held constant, let's say at 4 inches, how does the volume change with respect to the height changing? And that's what this whole problem would be saying. Okay, so now let's go to part B. Part B wants us to do the exact same thing, but assume that h is constant. Okay, so the derivative of the volume, so the change in volume with respect to time, and the constants I'm going to pull out, which in this case are definitely the 1/3 and the pi, but now h is constant, so I'm going to pull that off. And then here, let's take the derivative of the only variable on the right. So it's 2r dr dt. And if we kind of put this together in a common fraction then, dv dt is going to equal to, I'll probably write that as a 2/3 instead of just a 1/3, pi h, and then r dr dt. So this problem, they would probably say something like, if the height is kept constant, let's say at 10 inches, or depending on, I guess since we're looking at, looks like a cone, might be 10 centimeters, how is the volume change when the radius is expanded? And that's what we're looking at here. All right, so part C is how does the volume change when neither n or r or h is a constant? Okay, so we have to consider r and h both variables. All right, dv dt is equal to, let's pull off the ones that are constants, 1/3 and pi. Okay, right here now, we're about to ready to take a derivative, and since r and h are both variables, we have a product between variables, so we have to use the product rule. So first, times the derivative of the second, which would be then just dh dt, plus the second times the derivative of the first, which is 2r dr dt. and then kind of combining some stuff together, so we just make it look a little bit prettier, if you want to say that. So 1/3 pi r squared dh dt plus 2/3 pi rh dr dt. So this is an equation that we relate the change in volume with respect to both the change in the height and the radius of a cone.